In section 2.1, we're going to take a look at functions. So we are in chapter 2, and in chapter 2, it's all about functions and their graphs. So we're going to cover 5 sections this video, section 1. So what is a function? Before we actually define a function, let's define a relation. Now, in its simplest definition, a relation is simply a set that has at least one ordered pair in it. So let's say I have set A and my ordered pair, and for us the ordered pairs are numbers usually, but they could be other things as well. They could be names, they could be whatever. So but our focus would be on numbers. So here's a relation. So I got an ordered pair in it. Or I can have another relation. This one, suppose I have 1, 2, 2, 3, 3, 4. Here's another example of a relation. Or I could have names of people. So for example, each name associated with an employer. Now, what is a function? A function is actually a relation. Let's look at function C now. It is a relation. That means it has ordered pairs. And if the first numbers, the first elements in the ordered set are different, then that relation is called a function. So therefore, this set B defines a functional relationship between the elements in the first set of numbers 1, 2, 3 and the elements in the second set of numbers 2, 3, 4. Now the first numbers that we look at are called the domain elements of the set. So here my domain are 1, 2, 3, the first numbers. And the numbers in the second position, the ordered pair, would be like the Y component, the second component. 2, 3, 4 are the range values. So to make up, for instance, a set C here, that would be a function. That would be, for instance, -2, 0, 4, 0, and 5, 3. This is also a valid function simply because the first numbers are different. Okay, they have to be different. If they are the same, then that relationship that we portray, the relation, it is a relation, but it is not going to be a function. So remember, first numbers must be different. Now, something that is not a function, set D for instance. So this one, again, is a function. And I use FNC dot or period, short for function. Now, here's another set. Let's say this set is 2, 4. And let's go 2, 6. And 0, 7. Now in this relation, it is a relation. Everything you write down is a relation. So in this relation, note that these two numbers, the first same numbers, these are the same, correct? Therefore, this is not a function. Not a function. The first numbers must be different. So what if they're not different? What if we don't have a function? Well, clearly, if we don't have a function, then we cannot do the things that we are allowed to do with functions. So that's the big deal of it. Okay. So let's take a look at now an example. Okay. So for example, let's say I already gave you the set example. So suppose here I have a person, and I'm using just people here, not numbers. People, suppose I have James, Jeff, and I have, let's say, I don't know, Mary. Okay. And then here, I'm going to put their birthdays. Okay. Now suppose James' birthday is going to be on, I don't know, whatever, on June 5th. Okay, so it's going to be June 5th. And then both Jeff and Mary have, let's say they were born on the same day. Could be possibly different years, but the same day. Let's say this would be May 20th. Notice, as long as the first numbers are different, the first members are different, we have a relation. So this relation This mapping represents a functional relationship between a person's name and the person's birthday. Okay, so this 2 is also a function. Keep in mind, the first numbers must be different. Now, in this course, our focus, and particularly in calculus, our focus is on a very specific kind of a relationship here. So let's say we're going to define a difference quotient. Okay, so what is a difference quotient? Well, the word quotient means ratio, right? Division. And difference is just that, a difference. Now, to motivate this, let's say I have some kind of a function, and this would be like at some point x, and then some later point x plus h. So I'm going from x h units over. Now, right, left doesn't matter here really, as long as I go h units to the either side. Now, f of x would be the value of the function. One I didn't mention. We'd use a function notation. So we say f is, for example, the set 0, 1, 4, 2, 9, 7. So we use f for the function. Now, generally, we use an algebraic expression to represent functions, right? So, for example, we use f of x equal 3x minus 5. So that would be the algebraic expression. We are not always given a set, so we don't list the members of the set. Sometimes we just have an algebraic expression that represents the function. So 3x minus 5 would be an example of that. Now, in this drawing I have, let's say, so at x, the value of the function at x is f at x plus h. The value of the function is going to be f at x plus h. Okay. Now, if I look at the change in y, this is the change in y over the change in x. The change in x, of course, is h units, right? That would be the change in x. And if I simply look at the ratio of those two, then I have a quotient. Now, it's called a difference because the change in y is going to be f at x plus h minus f at x. And the change in x is going to be x plus h minus x. And of course, we can cancel the x's. Therefore, our difference quotient is simply f at x plus h minus f of x over h. Now, this may be a simple fraction, and it is a simple fraction, but it has really interesting consequences in calculus. Okay, so that's what the difference quotient is, and I'll show you an example of a difference quotient with specific functions in just a moment. The last thing we want to talk about in this section is operations with functions. And we're talking about the primary operations, the key operations with functions. And this is your addition, subtraction, and so on. So when we combine two functions, the addition of two functions, f of x and g of x, is written this way. What does this notation mean? That means f plus minus g of x. Of course, you only have either plus or minus. Chances are. So I'm combining both addition and subtraction of functions into one. We could multiply functions. Their product is notationally written like this. So f times g, both in parentheses, and then x in parentheses. That means first function times the second function. And we can also form quotient of functions. If we divide two functions, we write it this way. We actually conduct it in this way. Okay, so again, we have addition, subtraction, we have multiplication and division of functions. And in all cases, the domain is going to be, the domain of the resulting function is intersection of all domains. Intersection of domains of f of x and g of x. And in the case of a quotient, remember, division by 0 is undefined, so we're going to say here the denominator cannot be 0. All right, and there you have it. So let's take a look at now some various examples here. So let's say in my simple example, suppose I have a function f of x, and we're going to make this 3x squared plus 2x minus 4, and we want to evaluate the function at 0. We're going to evaluate the function at 1, evaluate the function at, I don't know, negative x, and we're going to evaluate it at x plus 1, and we're going to evaluate it at x plus h. All right, now another, by the way, impression of function, we can think of function as a relationship between input and outputs. Okay, so for example, let's say this is a machine, a function machine. Okay, and in this machine, the inputs, what goes into this machine, are the x values, and then the machine processes it according to some instructions, and the output from it is the function evaluated at x. This is going to be called the output. The input values make up the domain of the function, what possibly could be put into this function, to this machine to process. And the output, of course, is the result of the function working on that input. And that's going to be called the range, what comes out of the function. So in that sense, with this example, f at 0 means the input is 0. Therefore, we're going to replace x with the 0. And we simply do the arithmetic, and we get negative 4. So the relationship between the input and output is this. The input 0 produces the output negative 4. And we, for a single variable, which is what x is, our representation would be in the form of an ordered pair, x comma y. And this is what we mean here is x comma y. So the first number is usually the generic x. The second number, which is f of x, is usually the y values. All right. Now let's do f at 1. To do f at 1, you simply plug in a 1 for x and do the arithmetic. So for this one, that's going to be 3 plus 2, 5 minus 4. The output is 1. Therefore, the function or relationship between these two is 1, 1. It means input of 1 produces an output of 1. And next, let's do f at negative x. So f at negative x. Now, for this one, what we're going to do is the following. We have 3 times x squared plus 2 times x minus 4. So remember, the input is now negative x. So I'm going to put negative x here and here. Okay. Now, when we do, negative x squared is going to be x squared. 2 times negative x is negative 2x and minus 4. So there you have it. And that's going to be the new expression. And notice this expression is almost like what we started with the exception of negative 2x here, positive 2x there. So these are two different functions. Just because, you know, they have a lot of common parts doesn't mean they're the same. So those are two different functions. We did f at negative x. Now next, let's do f at, we're going to do it at x plus 1. So f at x plus 1 is going to be equal to, for f at x plus 1, we're going to replace the x's with x plus 1's in our initial function, right? So that's what I'm going to do. See, in here x becomes x plus 1, and in here this x becomes x plus 1. We simply replace with what's inside parentheses. And the next step, we have to carry the arithmetic. Okay, and to carry the arithmetic, or in this case the algebra, because I don't have just numbers. So we're going to square the binomial here. And when you square the binomial, let's do a review, quick review of squaring binomials. When you do that, you get a squared plus 2ab plus b squared. And you can verify this. That's just the formula for square of a binomial. Or we can set it up as product of two binomials. That's what a plus b squared means. Repeated multiplication of the same binomial by itself. And at this point, we're going to do distributive property, right? Which most of you probably know as FOIL method, right? FOIL. First, outer, inner, last products. But all FOIL is just distributive property. So A is going to multiply by A, you get A squared. A times B makes AB. And then that handles this part. Now above I have BA and then BB. That's going to be BA plus BB. A squared. Now AB, BA are the same. They're like terms, right? Because remember, in multiplication, order of products don't matter. BB is going to be B squared, and then you have the formula that we just talked about. Okay. And there you go. This formula is the same as that. So we got a couple of options. Either recall or memorize the formula, or you can create it on demand if you need it. However you do it, I'm going to expand this binomial. So when we expand it, now we're going to have x squared plus 2x plus 1, correct? And then plus 2 times x plus 1 in parentheses, right? That's going to be, it's going to be what, 2x, correct? Plus 2 times 1 is 2. There, we have that one. Then minus 4. And then we can distribute 3 to the trinomial and then combine like terms. So it's going to be 3x squared plus 6x plus 3 plus 2x. 2 minus 4 is negative 2. I'm going to handle that one. And this becomes 3x squared plus 8x plus 1. And there we have. That's the result of f at x plus 1. Notice we get a whole different expression. All right, so we did that one. Next, the last part of this exercise, we're going to do f at, this time we're going to do at x plus h. Okay, at x plus h. So let's do that one. What does it mean to do f at x plus h? Again, that means you look into the function, the original function, and instead of x, you replace the x's in the original with x plus h. You see that? So I have 3x squared is now x plus h, and 2x is 2x plus h. The original is up here. I plugged in for x into that one. All right, and then next we're going to do kind of what we did up here directly above it. We're going to square the binomial first, right? So let's square the binomial. We get 3 times. That's going to be x squared plus twice first by second. That's 2xh plus h squared. Distribute 2x, 2x, and 2h. We get 2x plus 2h minus 4. All right. And then we're going to distribute the 3 over. We get 3x squared plus 6xh plus 3h squared plus 2x plus 2h minus 4. And then in search of like terms, I don't see them. Each of these are different, aren't they? So there you have it. And that will be the result of f at x plus h. Again, we get this long polynomial form. And that's it. So we did example of f at x plus h. That's just evaluating function is what we just did. All right. Now, next, let's look at example where we have to find the domain of the function. So for instance, let's say my g of x is x over x squared minus 16. Now the domain of the function, that means what all possible x values. In the case of what we call this is a fraction, function. This function is defined for all values of x. You can choose any number you like. Plug in 0. You get 0 over 0 minus 16, and the result is 0. As long as you put in an input and get an output, then the number is in the domain. So the question is, in the case of fractions, how can we get division by 0? Because we know division by 0 is undefined. So for instance, 3 divided by 0 is undefined. So drawing from what I just wrote here, we're going to see what makes x squared minus 16 equals 0. Okay, now we can guess the numbers that make this 0, the numbers for x. So for instance, x squared must be 16, correct? And we can do by inspection. X could be 4 or x could be negative 4. By inspection means you plug in the numbers, and if it works, then you got it. So x is 4, negative 4. But then at both of these, we have division by 0, which is undefined, right? Therefore, what we actually do is that we change those equalities to inequalities. In other words, we're going to say that x cannot be a 4 or negative 4. Okay. Anything else is fine for rational expressions. Now we can write this in interval notation. Okay, interval notation uses parentheses and brackets, and here's how it works. If you look at the numbered line, for example, this is 0, my reference point. So we have negative 4 here, and then we have 4 here. Those are the two numbers that x cannot assume. So that means x can be anything else. Everything else here, here, and in this segment of the numbered line is fine. Now if you put infinity on the right, negative infinity at both ends of the numbered line, because remember the numbered line extends in both directions indefinitely. So from this I can actually write the interval notation now. So the x values, and we always go from left to right when we write these interval notation, left to right. Okay, so I'm going to go from negative infinity up to negative 4. Then we use parentheses if the value is not included on the number line. Remember, at negative 4 we get division by 0, so that value is not included. In other words, parentheses are our way of excluding these numbers. And then we're good from between negative 4 and 4, so we're going to use a union symbol. This U stands for union, and it literally means or. That's what it means. It means or. So what we're saying is the solution is in the lower part, or it could be in the middle part, stretching from negative 4 to 4, or it could be on the right side, anywhere from 4 to infinity. So that's what the interval notation is. Remember, with interval notation we use parentheses and brackets. Okay, and there you have it, the solution to this example. Again, for this one we want to find the domain. In case you wonder, what are we doing? Find the domain of that function, and we just did. This is the domain. Again, domain means what all can x be that you can process through the function. Okay, let's do, how about if we do another example of domain? So for instance, in this next example, suppose f of x, and by the way, f of x is generic f for function. It could be g of x, a of x, b of x, c of x, w of x, whatever. Could be something descriptive. So if I'm working on a height function, I may call it h of x, and so on. Now let's do this one. For this one, again, if we have a rational function, we're going to see what makes the denominator 0. Now, in order to see what makes denominator 0, I'm going to actually factor the x here So if the expression is factorable, we always factor it. It's easier to see what makes it 0 in the next step. Otherwise, it's harder to guess. So I'm actually going to set this equal to 0, but then I'm going to say it cannot be that, right? Because that gives me division by 0. Now, by 0 factor property, what is 0 factor property? 0 factor property. Some call it a theorem. By 0 factor property, it goes like this. If two things multiply to 0, right, then one of them must be 0. Then A or B could be 0. At least one of them, if not both, can be 0. So again, drawing from that, we get either the first factor may be 0 or the second factor may be 0. And remember, factor means multiplication. So when we have multiplication of two things, those things become factors. And there you go. So that would be in the domain, right? X cannot be a factor. This, set it equal to 0. And there you have it. Now, in let's use set builder notation. In set builder notation, X such that X cannot be 0 and X cannot be -1. This is called a set builder notation. And a notation means a way of doing something for us. In this case, a way of writing something. We can also go to interval notation for this, right? X cannot be 0 and it cannot be -1. That means everything else is permissible. So if I throw in infinities on both ends, now I can write the interval notation. Everything up to -1, union, -1 to 0, union, 0 to infinity. Remember, parentheses will exclude the numbers. So those cannot be part of the solution. And again, this is the interval notation for that. Okay. Now, what if, let's say I have something like f of x is equal to, is equal to x. This time I'm going to go x cubed plus x. So when I do that, actually, let me go x minus 1. Okay. Because I didn't want things to cancel, that's why. The other way I had it, I would be able to cancel the x's. I don't want to do that yet. And there you have it. Now, we're going to factor the denominator. It's going to be x times x squared plus 1. And again, by 0 factor property, each of those factors could be 0. So x is 0 and x squared plus 1 is 0. Now we're talking about real numbers here. In real number system, x squared plus 1, there is no real number. You square, add it to 1, you get 0, right? Because we know for this to be 0, shouldn't x squared be -1? Right? Subtract 1 from both sides and you will see that. There you go. But then how can I square a number and become negative? This is impossible. This can't happen. So the answer to this one, we just simply say at this point, this is not a real number. Later, when we talk about complex numbers, then it looks like the solution will be a complex number. But for now, that's it. The only real number that's excluded in this set. The domain is going to be all x such that x cannot be 0. You just don't worry about this part because that part is not real. Again, this is all domain. That's all we've done so far. Doing domains. Now, what if I have, let's say I have something like radicals. Okay. How can we determine the domain of a radical expression? Let's take a look at this one. My next example is, for instance, let's say I have h of x is equal to square root of 3x minus 12. Now, for this one, in order for this to work, for all square roots, remember the symbol square root means principal or positive root, right? Positive root of a number. In order for square roots to actually be legit, be valid, the radicand, which is what's underneath it, the radicand must be at least 0, right? The radicand must be at least 0, means greater than or equals 0. Other words, let's say I have a square root of -4. By definition of a square root, that means the answer. A number times itself gives me -4. Well, if I'm thinking 2 by 2 is 4, not -4. If I'm thinking -2, -2 times -2 is also 4. You see that? When we multiply a number by itself, it's always positive. So this could never happen. Therefore, we say that that answer is not real. Well, if it's not real, we're not interested in this chapter. Okay. And it's for that reason the radicand must be at least 0. Therefore, I'm going to set 3x minus 12 greater than or equals 0. And then I have to solve that inequality. I'm going to add 12 to both sides. Now with inequalities, remember you add, subtract. You don't have to change the direction of inequality. The only time you change the direction of inequality is if you multiply or divide by negative numbers. So for instance, if I have negative x is greater than 2, multiply both sides by negative, that means x must be less than -2. That's what we mean. So for this one now, 3x greater than or equal 12, divide both sides by 3, divide and multiply by positive numbers. We do not change the direction. So x must be greater than or equal to 4. Okay, and we can write that again in one of two ways. In set builder notation, that would be x greater than or equal to 4. Or we can use interval notation. To do interval notation, I always draw this on the number line. Now this time we have equal to 4, so you have a solid point here at 4, means 4 is part of the solution. And some books actually use brackets instead of open and filled circles like I have. Now greater than means everything to the right of it, right? Correct? And that goes all the way to infinity. Therefore the interval notation for this is going to be bracket 4 comma infinity, and we always put parentheses on infinity on both sides here and on the left side, because we don't know what infinity is. It's really not a number, right? Infinity again is more of a behavior of a number, not a number. It means very large, extremely large, and that's what that is. Okay. Now, if, for example, I had something like what I had up here, suppose, let's say my f of x is 1 over square root of 3x minus 12. So what we just did, all of this still holds. The radicand must be at least 0, means that holds. Except now, because this is a fraction, remember, the denominator cannot be 0. Therefore, at 4, when x is 4, we get exactly 0, don't we? 3 times 4, 12 minus 12, 0. So the domain of this one is going to be all x, so that x is greater than 4. You see that? I took the equality out of it, because when it's equal to 4, you have division by 0. So with radical expressions in the denominator, you have to consider both the implied domain of the radical and also safeguard against division by 0. Okay. Now let's do another example here. So in this example now, we're going to do, let's do operations. How's that? I'm going to make up two functions. Let's say f of x is root x, and then g of x is a linear function, 3x minus 5. we're just going to do our basic operations here: addition, subtraction, multiplication, division. So let's do f plus g of x. That's when you add f of x and g of x together. In this case, we have root x plus 3x minus 5, and of course no like terms to combine. That is the sum function. Now the domain of this function is intersection of domain of both f and g. G is a linear function. Linear functions can handle any x values. So the domain of g, and this is how I write it, the funny looking d means domain. The domain of g is negative infinity to infinity, right? Plug in any x, you will get a y for it. Now the domain of f, the square root, remember the radicand x must be greater than or equal 0. So in interval notation means 0 to infinity. Now if you look at the intersection of these two, the top one, the entire number line. The bottom one, let's say here's 0, can only take on things that are bigger than 0. So the intersection of the two regions, which is namely this region, is going to be the domain here. So the domain of this, the sum function, is going to be 0 to infinity. Although again, g is capable of handling negative numbers, but f cannot. So they have to compromise. They have to come together to where both functions can process the input. Okay, the difference works the same way. Let's do a multiplication, f times g of x. For this one, let's multiply them. So that means f of x times g of x. And f of x is square root of x, g of x 3x minus 5. And again, there you go. That's the product. It will have exactly the same domain as the one above. 0 to infinity. Okay. Now, let's look at the quotient function f divided by g of x. Now, because division or quotient is not commutative, like addition is, it's not commutative, or multiplication. Addition, multiplication are commutative, means the order doesn't matter. But in the case of subtraction and division, order matters, right? If I'm doing 5 minus 10, 10 minus 5, those are not equal, right? So that's what we mean. Subtraction is not commutative. Division is the same thing. 10 divided by 20 is not the same as 20 divided by 10. They don't commute. So let's say I want to do f divided by g, so it matters what goes on top, what goes on the bottom here. So on top I have f of x, which is root x, and the bottom I have g of x, which is the linear function 3x minus 5, and there you have it. What's the domain of this one? Well, the domain of the numerator again is from 0 to infinity. Remember, denominator, linear functions can handle anything. However, because we have a fraction now, we cannot divide by 0. So 3x minus 5 cannot be 0. That means at 5 divided by 3, x isn't allowed to be 5/3. You can try it. Put 5/3 on top, 5/3 on the bottom. The top is fine, the bottom you get division by 0. So let's take a look at now intersection of these two. Remember, the top goes from 0 to infinity. Anything is good. The bottom can handle anything except 5/3 now. What used to be the entire number line now excludes 5/3. It can't be part of it. Okay, 5/3 isn't allowed. So, what is the domain of the quotient? It's going to go from 0 up to 5/3, parentheses, union, and then pick up just to the right of 5/3 all the way to infinity. And that would be the interval notation for it. Okay, and there you have that. Now, let's finish this off. Let's finish it off with a couple of difference quotients, because again, difference quotients you definitely run into in calculus. So for difference quotient, suppose I'm going to make up this simple quadratic function, x squared minus 4. And it's simple. We want to find difference quotient, f at x plus h minus f of x over h. And in this quotient, by the way, h is always there. So it's a fixed part of this formula. What's changing is the numerator, depending on the function. So let's do f at x plus h. And we did that earlier, didn't we? Right in here, remember? We did f at x plus h. So it's not completely foreign to us. So let's do f at x plus h first. That means I'm doing f at x plus h. So this is going to be, remember, we're going to change x with x plus h. So that's that part of it. And f at x, of course, is the original function. So the numerator of this difference quotient will be x plus h squared minus 4. Then we have a minus. Let me use this different color minus here. So we have minus, and then the whole function gets subtracted. The original function was x squared minus 4. And we will divide this by h. So it becomes, now square the binomial on top, we get x squared plus 2xh plus h squared minus 4. And then the red distributes negative x squared plus 4. All of that divided by h. And now we can combine like terms. The x squares are opposites, they add to 0. A 4 and negative 4 add to 0, and that's as far as the like terms go. Now, in the numerator, I can factor the h from 2x and from the h squared divided by h. Dividing the h's out, so here we get 2x plus h, and that's the result of that difference quotient. You wouldn't expect to get a number out of this. You get an expression. Now, in this course, the concern is, can I handle the algebra like we just did? Well, let's say yes, we can. In calculus, they actually now do something with this expression. Okay? But for us in this course, that's as far as we're going to take it. But just know that this is an incomplete work at this point in this course. Let's try one last one here. I'm going to do the same thing. We want to do the difference quotient, except I changed the function. So I need to do f at x plus h. F at x plus h, you replace x with x plus h, correct? That's what f at x plus h means. This is the function. 1 is fixed, so here's 1. What's variable is the bottom. Instead of x, you plug in x plus h. And let's see. Okay, I was going to expand it. Let's go ahead and let's not do that yet. So my difference quotient now, let's work the difference quotient, is f at x plus h minus f of x divided by h. So I'm going to put 1 over x plus h quantity squared, that's this part, minus f of x, which is the original function, 1 over x squared. And then all of that divided by h. Now note what we have is what you would call a complex fraction. A complex fraction is when you have a fraction like this. That's the primary fraction line. And then you have secondary fractions here. You see that? So you have a fraction over possibly a fraction. So for example, 1/2 divided by 3/5 is a complex fraction. 2/3 divided by 7 is complex fraction. 5 divided by 2/9 is a complex fraction. So don't let that word complex throw you off. We are not talking about complex numbers. We're just talking about, I don't know why they call it complex fraction. It's maybe call it a complicated fraction, okay, to differentiate with complex numbers. But so here's what we have. Now, what do we do next? When we have complex fractions, in order to get just one fraction, not secondary fractions, we usually multiply the top and the bottom of the top, means the numerator, and the bottom is the denominator. We multiply by the LCD. In this case, we want LCD of x squared and x plus h squared. Okay, now the LCD of these two, the LCD is going to be x squared times x plus h squared. If you need to review LCDs, by the way, you can always look elsewhere on the web, but I also have on my YouTube channel, I have these in my college algebra class, I believe, and also I may have a few in my intermediate algebra class. Both of them are on YouTube. Okay, so let's say at this point we know that that's LCD, the product of the denominators. So what I'm going to do now is I'm going to multiply both the top and the bottom by the LCD. That means multiply the top by x squared times x plus h squared, and multiply the bottom by exactly the same thing, so you haven't changed the fraction. Now, in the numerator, we're going to distribute the LCD to the first fraction and then second fraction. Now, when we distribute to a fraction, let's say I have 5 times 2/3. When you multiply in something that's not a fraction by a fraction, you can write 5 as 5 over 1 and then times 2/3. And here now we multiply the tops, we multiply the bottoms, correct? So going back to the original, when we multiply a non-fraction times a fraction, only the numerator is multiplied by that factor. So here I multiply 5 times 2, 10 divided by 3. You don't multiply top and the bottom by 5, just the top, right? Only the top. So we're going to do the same thing with this algebraic expression, because I'm about to multiply by a fraction on top. So I'm going to multiply LCD times the first fraction, and when I do, I will get x squared, x plus h squared. It only multiplies by the top. And the second fraction, again, it only multiplies by the top, which is just the 1, divided by x squared. And the denominator, I'm just going to write it as h times x squared, x plus h squared. I just moved h to front. That's all I did. Right? Remember, multiplication is both commutative and associative. That means if I have ABC, BAC, CAB, these are all the same products. So that's what I just did. Moved h to the front. Now, at this point, let's see, how did multiplying by LCD help us here? Well, in the first fraction, I have common factors I can cross. And in the second fraction, I have common factors I can cross, right? So what's left? In the numerator, I simply have x squared minus x plus h squared over everything in the denominator. Although the expression is more complicated than what I started with, perhaps. However, if you note, I no longer have a complex fraction. I have just a simple fraction, a numerator and a denominator. Next, I'm going to expand the binomial. So it's going to become x squared plus 2xh plus h squared. All of that divided by h, x squared times x plus h squared. And if you distribute the negative to all three terms of that polynomial, what that will do is it will create a couple of opposites, namely that and that one. The negative still distributes to the remaining two terms. So this is going to become negative 2xh negative h squared divided by h x squared, x plus h squared. So the expression did simplify somewhat. And the final step, the final simplification is in the numerator. Notice the h is the common factor. So I'm going to factor the h in the numerator. That will give me negative 2x minus h. And in the denominator, I have h, that's this h. And then, of course, I have the remaining factors, x squared and x plus h squared. And I can cross out the common factors, and there you have it. Now we can really go fancy if we factor the negative from the numerator, right? This is going to be negative 2x plus h over the denominator, x squared, x plus h squared. And there you have it. Note again, we don't expect a number out of this. We simply expect an expression that we got. And there you have it. This will solve this example. And that's about all we wanted to do in this section, folks. So everything you wanted to know about functions. And there it is. Thank you for watching.